think a good shout in this question is first of all to add each row up and see what we get. Do we get any multiples of 3 straight away? Here we get 16. 21 plus 16 is 37. 22 plus 8 is 30. Here we get 49. Now, that means that we need to swap at least two pairs of numbers to be able to get a multiple of 3, because if you just swap, say, I don't know if this is even going to work, but if you just swap the top and the middle, then you might sort them out, but then the bottom would stay the same. So we're going to have to somehow do two pairs. Now you can go ahead and probably figure that one out, but I want to share with you a method that's really effective and is going to be useful for more complicated questions in the future. Instead of writing down the numbers in the table, we can actually write down the relationship to multiples of 3. For example, 7 divided by 3 is 3 remainder 1, meaning that we are 1 more than a multiple of 3. So I'm actually going to replace my 7 by 1. 5 divided by 3 is 1 remainder 2. That means I'm 2 more than a multiple of 3, but I'm also then 1 less than the next multiple of 3. So we can either write 1 for being 1 more than a multiple of 3, minus 1 for being 1 less, or 0 if we got a multiple of 3. And this greatly simplifies the table. So I get minus 1, 1, 1 more here. This one's 1 less, this is 1 more, and this is, oh sorry, 22 is actually 1 more and 1 less. So if I now sum up these rows, I can see that I'm going to get 1, 1, and 1. And the aim is to make them all 0. But it's quite quick then to see how we can make them 0. Because what I could do is I could swap around these two. Because then it would become 1, 1, 1, and minus 1, 1, minus 1. So now I'd get a 0 here. And you can maybe see it from here, but I don't know. I feel like it is more difficult on the left-hand side. Now that's all well and good, but now I've ended up with minus 1 for the middle one. So I need to actually balance that one out. And I could do that by getting another minus 1, actually. So then this would then become minus 1, and this would become plus 1. And suddenly we get a 3 when we add these up, but that's the same as 0 because that's a multiple of 3. Here we get minus 3, but that's 0. And here we get 3, so 0. So the smallest number of moves needed, like I said right at the start, how it had to be greater or equal to 2, because there's no way we could get them all to be all the same just with one swap. But I have now shown how we can do it with simply 2 moves. So that is, I did the necessary condition, then I've done the sufficient condition. So we swapped the 5 and the 16, and then we swapped the 10 and the 8. So our final table with the numbers in would be 7, 16, 4, which gives 27. And over here, 11, 8, 5, which gives 24. And at the bottom, 22, 19, and 10, which gives 32, 42, 51. Right, this is a nice idea that I've used here. And like I said, you can get away without it, but it was a good time to kind of bring in such ideas because there's a topic known as, essentially we've been using modular arithmetic. So 7 mod 3 is equal to 1 because it's saying what do I get as my remainder when I divide 7 by 3? And then something like 5 mod 3 would actually equal 2, but you could equivalently write it as minus 1. So there's more than one answer. And it's like we're using clock arithmetic, really. Once we, on well, an analog clock, the hour hand goes around and you start at, well, you're at 12, and then you go around to 1, 2, 3, all the way around until you get to 12, and then you start again. Essentially, on a clock, you are using modular arithmetic because you have the number of hours since the dawn of time or whatever, or since some starting time, but then we always actually only count up to 12 and then start again. And what is then changing, obviously, is the day, the dates, the month, the year, and so on. But that is another example of modular arithmetic. So I strongly recommend looking into it because you will see it on later math challenges, and it's really interesting. And I've used it here to good effect.